And this is me. I fly around a lot, so if I waddle back and forth, it's because I've probably been sitting on an airplane for 12 hours. I got back from Paris on Monday and then flew here. I live in San Francisco, by the way. But I am really excited about this talk because it hits in an area that's I'm really passionate about. It really talks about, we're talking about tooling, right? We're talking about how a development tool that we use can impact the way we work. And that's really important to me because there's a computer scientist from many, many years ago that wrote this paper that I think is one of the most underrepresented pieces of knowledge that we have in computer science. So that comes from Melvin Conway. Sorry, this is kind of terrible, by the way. I will try to explain what's on it. So Melvin Conway wrote this paper, How Do Committees Invent? And so what he was talking about is communication structures. And way at the bottom, and this is the thing that spreads the most, way at the bottom of the paper is what really comes around as the most important part of this. And that becomes what's known as Conway's Law. And Conway's Law says that our communication structures will be reflected in our software design. So the way we talk to each other and the way we communicate with each other's teams will be reflected in the way we write our software. So the classic example is if you have four teams working on a compiler, you will have a 4-pass compiler because they are working in this system. So the idea here is that our tools can dictate the way we communicate. And that's really important. And this is something that isn't really new. This is something that was from 1968. We're still solving this problem 36 years later. And I think it's really important to pay attention to it because communication structures is what we're really trying to get at. And when we're coding, that's what we're doing. We're trying to communicate to either our future self, in 6 months so that we don't kick our own ass for not understanding what the hell we were thinking, or communicating to someone else's team. This is very much not about just writing software and using source control. This is about communication. And you're probably like, wait a second, this is Git and it's a tool, right? It's source control. It's nothing more than that. But I don't think that's true because I think tools define our communication. Think about all the things you use in your company. If you're an email-heavy company, I bet you communicate in a very particular way. If you're an IM-heavy company, you communicate in a different way. Those tools allow you to communicate in different functions. And so the way we communicate defines the way our cultures are. If we have these very rigid lines between the way we communicate, then we will also have these very rigid lines inside of our companies, very hierarchical systems. But what that means is then our tools define our culture. So how do we use Git, for example, within our development cycles? How do we use our text editor? How do we use all of these other flame-war-y type topics within our development cycles? And how does that change the cultures and what does it say about us? I'm a big fan of a website called Uses This. It's just a blog. Every twice a week, I think, or so, someone gets profiled about what they do, the tools they use. I like it because it talks about what that person does. In the same way that you can dig up an ancient civilization's bowls and arrowheads and find out and understand what they are about, we can also say the same thing about the tools we use as software developers, right? The fact that I'm a Rubyist says something about me. If I'm a Java developer, that says something different. If I use Git versus SVN, that says certain things. Not good nor bad, it just means that I'm stuck in these particular paradigms that I have to work, and so that's going to define a lot of things. So I am Chris Kelly. On the internet, I go by Amateur Human. That's Twitter, GitHub, SpeakerDeck, Gmail, basically anything you can think of. I'm most likely the Amateur Human that you're finding there. So feel free to reach out to me there. I work for a t-shirt and sticker company called GitHub, and we also make source control solution, but mostly stickers and t-shirts, so if you're interested in any of those. And if you didn't see it yesterday, we also announced a 5-inch figurine. It is not a toy. It is a figurine. We cannot legally call it a toy. Has parts that'll fall off and choke children. So definitely get your hands on one of those. They are pretty amazing. We've had them in the office for a while, and we've been so excited to get them launched. So now if the source control thing never works out, we're literally just going to go sell t-shirts, stickers, and figurines around the world. It seems to be fine for us. I'm also one of the co-founders of an open source organization called To Do. This was founded by a number of tech companies that were trying to understand how to open source software. Because the nuances of open sourcing a piece of software as an individual is very different than what goes into open sourcing as a company. The way that we have good maintainership, good growth of our communities, how do we transition them off to the communities when we no longer want to maintain them full time, things like that. So we're kind of just getting up and running, but nonetheless, we are trying to publish information. So if you are in this space, check out the todogroup.org and the things that we'll be talking about in the next year or so. It's pretty exciting. And Will in the back is poking his head out. He is also one of the co-founders. There's a couple of us here this week. We're most likely getting together if you want to talk about this kind of stuff, about how your company can get into open source. Come find me at the break or at the booth, and we can start to chat about that stuff. It's going to be pretty awesome. But really, we're here to talk about productivity. Like, how do we get better with Git and GitHub? So let's do some polls, because I like polls. How many people use Git day to day? Over half. How many use it at work day to day? It's almost the same amount. That's good. And how many people use GitHub not for just downloading stuff, but for actually production work day to day? A little less. You're probably using some other Git server, Gitolite or Gitorious or GitLab. Those are all okay. Stash, Bitbucket, all fine. This isn't a GitHub talk. It's not about selling you GitHub. It's about just how we can work better. What we want to talk about first, though, is how you use source control. How many people use source control something like this? You just, hammer out some code for about an hour, git add everything, commit it, and you're kind of done. That's Git as source control, and that's fine. But all you're doing is controlling your source. That's all you're doing. If you're using a tool like this every day, it should probably serve a better purpose than simply just tracking your sort of arbitrary changes throughout time. It should probably be part of your development cycle. So Git is source control. It's this pretty awesome, decentralized, fast thing. If you're an ex-SVN user or a current SVN user, there's some nuances that are different about it. But to me, Git is much more than that. Git is a communications tool. Because Git works on a line level, so an individual line of code within a file changes. It can track where that goes. Whether that line gets moved up in the same file, it gets moved to an entirely different file. SVN is different, where it's tracking based upon file. So now that we can track in Git the individual chunks of code, instead of just an entire file, hey, I changed this file, something in it changed. We can actually say, I changed this method or this function. And then I can really start to talk about why I'm changing these things, how I'm changing. I can start to communicate while I'm doing this about what's going on. And I think that's really important. If we're doing it pieces at a time, then it's more of a journal about what we're doing and not just a source control log of hey, I did this fact. I can see that. That's not that interesting. But why you did it becomes the interesting part. But I bet you didn't know Git is also a debugger. Git has a pretty awesome tool that I think most people don't use day to day, or at least I use it a couple times a year probably, and it's one of my favorite things, and we'll go over it depending on where we end up in the timing, whether the end of the session or the next one called Git Bisect. If you happen to miss it, I highly recommend looking into it. It's amazing. Git is also an enforcer. How many people hate white space at the end of their lines? How many people have a team that's like, oh my God, you left white space at the end, or you didn't put a new line at the end? Git has a system that can enforce these rules. It can flag users so that they can't push code that violates various requirements. Ideally, it's not something as arbitrary as white space at the end of a line or a new line at the end of a file. But Git is an enforcer. We have an Octocat for that. Git is also automation. You can tie Git into any number of things. There's a whole scripting system that allows you to do pre-commit and post-commit hooks. I can use it in my build system to close issues, open issues, automatically run builds. It makes my life easier. I've never met a software developer that doesn't want to automate their life. So Git is a perfect tool for that. Something that's important to know, though, is Git is not linear. So in the git commit, git add dot, git commit blarg, that's literally just a linear system, right? You're just thinking about your code as I did this step, step repeat, step repeat, step repeat. But Git's not linear. Git allows you to move around files at any given time to do anything you want. And that's an important thing to know, because it means that you can start to play when you're working and not just work. You can experiment with your ideas. You can go and break the hell out of your code, because you can always get back. It doesn't matter where you ended up. If you ended up in some like broken state, Git isn't ever destroying data. On very rare occasions, you'd have to really try hard to destroy data in Git. Almost everything you do is adding data to Git. Even removing files is actually just adding more data. It's a statement about, I'm deleting this chunk of code, and this is the timestamp and who I did it, even though that code still exists. The other thing to note is Git is also not permanent. So the only time you can ever really destroy the world is if you're rewriting history and forcing it to servers and then forcing everybody beyond that to download your forced changes. Nothing in Git is permanent. You can always undo it. You can always get your source code back. It's not a pain in the ass. It makes Git is so fast and light and branching is so easy that you should be comfortable just screwing around and looking at ideas and trying stuff out. So don't be afraid to do that. Don't be afraid that this code has to be perfect when I commit it, because you can go back and rewrite what that commit message was. You can go backwards in time and start over, and then go forwards in time. That's a really exciting opportunity, I think, when it comes to software development. Something you should note, though, is for anyone that's new to Git and GitHub, is Git is not GitHub. GitHub is a tool built on top of Git. We add all kinds of niceties and great features, I believe, but it is not Git. So Git is a command line system that was built just under 10 years ago now. And GitHub was built a few years after that on top of it. So when we're thinking about this, it's becoming less and less of a problem now that there's a confusion between Git and GitHub, but there still is a sort of confusion every now and again. So in case anyone is in the room that isn't quite familiar, Git is a tool and GitHub is a service built on top of that tool. And we'll get into how those differ a little bit. So let's talk about Git, because that's really what we're going to spend most of our time talking about. Git. There's a bunch of GitHub stuff in here as well, but most of the time we're going to be talking about Git. So Git was built in 2005 by Linus Torvalds, the creator of Linux, if you're unfamiliar with who that is. Next year is the 10-year anniversary, and so ideally we'll be having a fun conference and event if you want to come to that about Git, and Git, which is called Git Merge. We did it 2 years ago, or a year ago now, and so we'll do that again. After a few months, Linus gave up on Git. He was like, he didn't have the time to work on it. There's an individual that took it over just a few months after initial launch. His name is Junio, works for Google, I believe. And they built it very much like they built Linux, where everything is basically a file. So there's a lot of similarities, and you're going to start to see how we're actually really just navigating file systems when we're looking at the Git internals, and not any sort of magical database that is mystical and a little hand-wavy. It's really straightforward. Git is a very small, fast source control system, unlike SVN, which can be cumbersome. Everything is local, so if you change stuff on your system, it's not going to affect a server. You don't need to check out code from a server to work on it. You can just work on it. It's yours. You can do whatever you want with it. There's no technical central system that you have to be connected to in order to use it. That's why it's a decentralized version control system. And Git is very fast in its branching system, because it's just adding a little bit of data when you go to a branch versus like cloning an entire repository every time you do it in an SVN. So GitHub was founded in 2008, trying to solve a problem where there was very difficult ways to share code using Git. Git was an amazing source control system, but had very little ways to share code. It was a lot of emailing files back and forth, patch files. The Linux kernel is actually still developed this way, where you're emailing a patch file up to a mailing list, and that gets then brought in. So GitHub was developed in order to solve this problem, to create a central Git server, so that you can then push your code to that, and then I can pull your code down. That way you don't have to know who I am. You don't have to know who I am when I want to contribute back to you. You don't have to know who I am when you want to send me something. I can just get it from this centralized system. Even though Git is decentralized, GitHub has created a space in which you can then share code very easily. And I think the biggest contribution that GitHub has made to this space is the pull request. How many people are familiar with pull requests? How many people didn't want to raise their hand? So most people are familiar with pull requests, and we'll talk a little bit about them in a little later. So I think the pull request made contributing to open source the easiest thing possible. But GitHub isn't the only solution. You can use the web interface. There's the CLI for Git itself. If you are on the, that's a terrible projector. If you're here for the front end track and you're not comfortable using the command line, we also have GitHub for Mac, which is a GUI client. We also have GitHub for Windows. If you are a Windows user, this is probably the easiest way to get Git into your Windows machine. It's a nightmare otherwise. Even if you don't use the GUI client itself, use GitHub for Windows, and to install Git is probably the best thing. So those are a couple other ways. There's also any number of other tools, graphical interfaces that allow you to interface with Git and GitHub. You can use those as well. Cool. So let's go inside of Git. What we're going to do is take a look at what's underneath Git. You're probably familiar with a lot of commands like git add and git commit, but what's actually going on when you're doing that? So we're going to deep dive into that a little bit. And that's important because I don't want you to have fear about what you're doing. I want you to have an understanding of what's going on underneath. I don't know why I have an affinity for this kind of like spelunking into code. I spelunk into the Ruby code in the garbage collector because I'm weird and it's like 16 layers deep of turtles all the way down. Git is kind of the same way where it's just like all these obscure things. But I think once you hear it once, it demystifies it a bit and you don't think Git is doing magic anymore. I thought Git was kind of magical for a very long time until I started spelunking. So that's what we're going to do for the first bit. And then, like I said, if you have questions, if you get lost, we can pause and talk. So don't be afraid for that. So first, git init. You're familiar with that. That creates an empty repository. That's pretty basic. It's going to create a file system that looks a little like this. So for the people in the back that can't see it, there's a couple major components that are important and then a couple extras that you don't really care about. So inside of a Git repo is the most important parts are the head, which is the top file you see there. And then you've also got objects and references, a directory of those two things. Also in this repo, also in this directory structure, you have the configuration file, which is config. It's sourced for this repo's configuration alone. You can also have global ones. Then there's also a built-in web client in Git, and so it pulls the description. That's what the description file is giving you. And then info holds the ignore file. So files you don't want to pay attention to, that you don't want Git to track. So for our purposes, the things that are most important are head, objects, and refs. That's what the core of Git is built on top of, those three components. So let's add something to Git. So we're going to just echo out a text string, all things open, and then we're going to hash it. So Git stores everything as a hash, and this is a 40-character string that gives it a reference. It actually is calculated by something, so this hash will be the same on my system as it is in your system. But it's just going to output a 40-character SHA, and then we're going to just, and the flags we're using are, we want to write it, so that's the -w, and then we want to take it from standard in. Otherwise, it is expecting a file path of some kind. So we're just going to take in all things open and restore that. That's all we've done. Nothing special about that. So when we look at our tree now, we can see that we start to store the object itself in the database. It's a flat file system database, so it just creates a file structure. In this case, it takes the first 2 digits of your hash, uses that as a directory, and then puts the rest of the blob itself into the other 38-character file name. So that's what we've got. We've stored all things open as just a string in our database. If we look at it, we can use a Git utility called cat, which is basically the same thing in Linux or in any Unix-based system, to look at the file structure. So if we pass in cat, the p flag is how we get the contents out of it, and pass in the hash that we created, then we can see all it is a text string, all things open. Nothing special. So let's go ahead and add a file, MIT license, to our create a license file. And then we're going to add that file to our hash, basically doing the same exact thing as we did the thing with all things open. In this case, we passed a file itself rather than a standard in. Something to note, though, is that we didn't add this file. we added this file's contents to the system. So the only thing we have now are two blobs, one that contains the structure of all things open, and the other one that contains MIT license, the words MIT license. That's it. It doesn't actually contain any files. And that's interesting, because when we look at the kind of file types, again, we're using cat and passing /t to see what type it is. All we're doing is storing file. All we're doing is storing content. So Git has an understanding of content apart from file names, apart from actual file systems. SVN is very different in that way, in that it understands files. Git understands content. And that's where we start to understand how Git can move lines amongst the same file and still think they are different components, because we're looking at content rather than actual file systems. So when we combine a file content with a file name, that gets something that's called a tree in Git. So let's look at what a tree looks like. So what I'm going to do now is I'm going to take that blob that I had, the license, the MIT license blob, that text. I'm going to assign it in the Git database the name license. This is the blob reference, so it knows what content I'm going to put into that file. And I'm going to give it the 644 permissions in the Unix file system. And then I'm going to add it to our database. So now I actually have a file called license in my Git database, something I didn't have before. So now I'm going to write that out into the tree. So I'm going to store that, and that's going to give me another hash. If you can see that, it's basically hashes all the way down. It's just references upon references upon references. So if I want to take a look at the hash itself, I can look at that again, and you can see a couple things. So now you can see when I call out the hash for the tree that we just saved, the file name and content combination, you can see that we've got a 644 file. It has the blob of D1, yada, yada, yada in it, and we call the file license. So as we change the contents of license, this will look the same, except for the blob reference will be different. That hash that's referencing the blob will change over time as the contents of the file license change. Even though we still will have the same reference, we'll still use the same tree reference, we'll have a different connection to it. So let's do that. Let's change the license to an Apache version 2 license. I don't really care what your preference is. I'm pragmatic on licenses. Let's not have that fight. So what we're going to do is we're going to output the license. We're going to update the index with a new license file in it. And then we're also going to add a new source file, just an arbitrary source file that's on this file system. So let's take a look at what that tree will look like. So now let's write all that out. So what we've done is change the license content, as well as added a new file. And now we've saved it. So we've written out to the tree and gotten ourselves a new hash, which is right there. So 9B1 something or other. So if we check out that, you can see now we have two things. We have a license file with a different hash to the blob, so it's pointing to a different set of content, as well as a source file with its reference to its blob, so its file content. So let's dig into this a little bit. So if we use our cat file to look at the contents of that blob, you can see that our license file now says Apache 2 in it. We've got data under source control now. That's basically what we've done. But the problem is, does anyone remember all of those hashes? I don't. I can barely keep up with them, and I'm looking at the stuff all the time. So that's where a commit comes in. Commits are references to things of spaces and times and references to each other. So once we've got our blobs and we've got our tree, which is a blob plus a file name, then we move on to the commit. So let's make a commit. So let's take the tree in which we originally had, which was the license file and that source file. Remember, we output that. This is the 91B hash for it. So let's commit that tree and with a message of initial commit. And that's going to get us another hash. It's hashes all the way down. So we're going to then update our index with a new file. I'm going to include a new one. I'm going to write that tree out. And then we're going to take a look at what our new tree looks like. So I've got a commit that has our license and our source file. I've written to our history the inclusion of a new tree which is a header file inside the includes folder. So you can see on this one, as we look at the hash for it, we've got tree instead of blob, which as we've seen previously. So trees are just structures nested within each other. So if I want to look at that tree, I can just call it, or let's commit first. So we're going to commit the tree that we just did. What we're doing here is we're adding the header file, which is in the includes directory. So that's the tree that we got when we did that. And we're pointing it to the previous commit before that, so that now there's an ancestry to it. So if we look at the hash that came out of that, let me find where we're at so you can see. So we're at 532D, yada, yada, yada. So if we look at that hash, we can see that these things are now committed and connected. So we have our initial commit, and then we have our header commit that we just did. So there's a lot of labor for sort of very little effort, a little reward, I guess. And so what we've basically done is develop and manually do all of the commit and the add system, that the sort of the external interface in which Git provides you. When you do a git add dot or a git commit and then a message, we've recreated that using Git's low-level commands. So let's take a look at what's inside of these things and see how we can bury down. So let's take a look at the commit file that we got. So we got the commit hash, which is the 532D. You can see that it's got a reference to a tree. That's the reference to the file system structure that it was. The parent of the commit that went before it. Information about the committer and the author of those things, as well as the commit message. So let's dig in. Let's start drilling down backwards to walk through the file system. So let's take a look at this tree, the file system that came from it, right? So you can see that in our tree, we've got our license file, our include that includes the header below it, as well as the source file. Let's look at that tree again. Dig further down in the tree, you can see it's just a blob with a content reference and then the header file name. And then we can actually look at the blob itself and see the header content. So we can drill all the way down and walk this information very easily. And visualizes like this. It's probably a little easier to kind of get an understanding of. So you can see that we started at this very top commit and worked our way down. So we're expecting the commit, then we inspect the tree. The tree shows us that we have two blobs and another tree. We inspect that tree, you can see that tree has another blob hidden within it. And it's just literally just walking all the way down. I don't know if you guys this thing is colorblind apparently. This is red on the laptop. That's kind of weird. Or either that or I'm colorblind. So we've basically created git add and git commit. Any questions so far? Yeah.
So why should we have multiple blocks?
Yes.
You said tree is pretty much the content associated with the file name.
A tree is a file name as well as references to the file structure. So in this case, this tree, which is the outer tree, includes the include directory, along with which includes the header file, as well as two files themselves on that level of the tree, right? So in this case, license is pointing to a blob, which is named that, with the contents of Apache v2 in it.
So if I think about day-to-day work, I just Google it, come in and use it. I have no idea.
You wouldn't. So yeah. So the.
I come here. For example, I come in the file, and the file is supposed to be a blob. I either my branch, which would be a tree, I guess.
Yeah, so the file will have a blob, which is its contents. It'll also be part of a tree system, which places it within the directory structure. As you commit it, it actually ends up getting all the way up to the very top, where you get metadata about who committed it, when it was committed, components like that. So it works its way back up. Yeah. So this is all low-level stuff that you would never use these commands for anything day-to-day. That's what git add is for and git commit is for. It's doing all of this stuff for you in the background. But it's important to understand that basically the file structure is very straightforward. It's not mystic on what's going on. If you inspect these files on your actual file system, this is what you're going to get. You're going to be able to see where your data changes, why it's changing the way it is as you kind of move around. And you'll see why we want to move around in a little bit.
These blobs are basically file level changes, right?
Yeah, they're line level changes, yeah. They're content level changes.
So how did we initially committed a different license type and now we changed that? Is that also tracked in these blobs?
Yeah, so that's just further up in the tree hierarchy. We didn't explore down that way. So this commit, which includes the header, doesn't include that commit. So as we explored down from the top commit all the way down, it skipped the fact that we changed the file type at some point in time, but that still exists.
So each commit has its own sort of tree structure.
Yep. Yeah, exactly. Sure.
How does the hash change?
It's a SHA-1 hash. So it's actually made up of a little bit of a header, which is the file type. So in this case, a blob or a tree, and then a checksum character, as well as the file contents, and then that generates the SHA for it. That's why it's exactly the same every time. And then there's a null terminator character at the end of it. So that's why it can be the same on everybody's system, because it's just an algorithm based upon that. Cool. All right. So hopefully you're not too lost yet. We're gonna dig down, and then we're gonna work our way back up the system into more higher level topics. So this is really a giant pain in the ass if you were just if you had to manually do all of this stuff. We've added all of this functionality like git adding, git committing, navigating around it. But it'd be really hard to navigate your history if you didn't have references. Every time you commit, you'd have to remember what was the previous commit you wanted to attach this one to, and then go from there. Inside of Git, there's an entire reference system that basically tracks this stuff for you, so that you don't have to really worry about it. So inside of the refs folder, so we were just previously looking at the objects folder. Now we're looking at the refs folder. There's two major components. There's the refs heads and refs tags. And everything else in Git is a file, so are these. These are literally just file pointers pointing around. So if I want to call something master, if I want to have a reference to master, there's a low-level command called update ref that does that. And I'm really just literally embedding it into this file system, refs, heads, master. And I give it a SHA in which it's referencing. So master is now that SHA. It's pretty straightforward. If I take a look at my log now, I can, instead of doing a git log and the SHA name, now I can do git log and master. And you can see I pass in the commit, and then it gives me the history based upon that, because everything's referencing each other. If I look at that file, all it is literally just a file with the SHA in it. That's all it does. This is actually what makes Git really, really fast. POSIX systems are very good at opening and closing files very rapidly. And so rather than using symbolic pointers and whatnot, literally it's just a text file that has the SHA information in it. It's pretty neat. And you can technically edit this file and put another one in there. Don't do it, but you technically can. It won't break anything, but it's not recommended. So if I want to add another reference, I want to have a initial branch in our typical language. So if I want to make a pointer to my initial commit, then I can add another reference to initial, and I just add the commit SHA for that. Pretty simple. And so when I do log initial, all I'm doing is I'm getting that first commit instead of both commits. That's pretty straightforward. So this is what our trees looks like from now on. So you can see there's one unique thing outside of objects and refs that's really important to get, and that's called the head. It's the very top file that you see in the file system. The head is a reference of where we currently are. What does our file structure look like? And then head is going to get called by other functions. So when I do a git commit, it's going to look at what is the head, use that to find out what the parent commit is, and then add that on and tack on so on and so forth. So head is really just another file system. So let's check out our initial commit. And then we're gonna take a look at head. And you can see it's just a reference to the initial branch that we created, the ref of initial. So now we're on, our head is initial, And anytime we're doing other commits and other changes, we're always referencing this file to find out where we're at so that we can have these, so we can have these sort of automatic functions happen for us. Let's quickly go through a couple things and we'll take a break in 5 minutes. So the last bit is tags. A tag is a unique kind of reference that is much like the references we were previously seeing. But now what we're seeing is a tag is referencing not a moving history, but an actual file at an actual place and time. So tags are typically often used for releases. So if you want to say all of these files are at v01, then now I know that these files, this will never change, and I can always reference these files at this place and time. Whereas my branches will always update themselves as I'm changing the file system, or as I'm changing the content, right? So master will always update as I add new content. Initial will update as I do that as well. Tags, on the other hand, always stay permanent. One really useful thing for tags is that you can reference a specific file. Again, references can reference anything. It doesn't have to be a commit. It could be a file blob. It can be a tree. It can be, in this case, we're doing a commit. So one of the interesting use cases is in the Linux kernel, the PGP key of some of the committers are referenced as tags so that they're easily pulled out, and then you can use those to sign code and verify code based upon that. So a tag is really just something very basic in that it's just a reference to anything else. So this is what our tree looks like. So we've got, our refs folder has initial and master files in them, as well as we have a tags file. And those are all just pointers to other things. All right. Again, this is supposed to be red, by the way. So let's do one last thing, and then we'll take a break. After the break, we're going to get into a lot more of the high-level functionality of Git and GitHub and whatnot. And this will be if you didn't know anything about Git before this, you will basically have everything you need to know. So getting code is the other thing that trips up, especially new people, about all the different areas in which code can exist. So traditionally, if you're working on a project inside of your company, you need to get that code from your company's repository, whether that be on GitHub, your own internal servers, some other service provider. But you need to get that from somewhere. So that's in the amazing cloud that we all have icons for these days. And then I have my local file system represented by my laptop. So, excuse me. Inside of my project, I can clone a file. I can clone a repository. Traditionally, this has a much longer URL, but I didn't want to extend it out, so just imagine this has a URL on it, not just a reference in this way. So I want to bring down the code from my server down to my local repository. So this is a Git clone. GitHub created a construct called a fork, which is basically a clone that's being done on a server. So if I fork code on GitHub, I'm making a copy on the remote server for me to work on, and then I'm going to clone that part down. We also add some sort of references to other repositories that are clones of that, so you can see network graphs and whatnot. But if you're ever confused on what a fork is versus what cloning is, they're basically the same exact thing, except for a fork is being done on the GitHub servers, whereas here, we're cloning down to our local file system. So we have three areas that our file system contains. We have our working directory, our working environment. We have our local environment and our remote. So working is untouched. It's the stuff that we can play around with. It doesn't exist in history in any way. Local is things that we've actually committed to history, but we only exist on our file system and aren't yet back on the main server. And then remote is a mirror, is a tracking mechanism for what's on the server. So there can be points in time where you have things in working that you're currently done, changes you've committed that are on your local, but you have yet to be pushed up, and then things that have all been pushed up, and that's how we track between remote and the server itself. So let's edit our file, whatever edit does. We make a change to the file, the README file. We're going to add that to our staging environment. So we add that file. Then we're going to commit it. So that's going to move that file out of our working environment and putting it into our local environment. So now we actually made it a commit, and now it's in our Git history. Now it's in our Git database. But it doesn't yet exist on the server. So we need to push it to the server. So now that file is then moved, is tracked both in the local remote that we have, the one that's the tracking system, as well as actually on the file system itself, on the file server itself. So that's what git push is doing, is all we're doing is saying we've made this go from our local system into the remote system and actually pushed it up to the server. So sometimes changes come in from another developer, and you need to bring those down. Git fetch is gonna bring it from our file system into our remote. A lot of the times you're going to be working and you're in the middle of a project and you don't want the changes from other software developers put into your system yet. But you do want them because you might be getting on an airplane and you don't have access to the file system when you're on an airplane. So you might want to fetch those and bring them locally so that they're actually on your physical system, but not within your working system. So you wouldn't see those changes yet, but you have access to them when you want them. So git fetch is going to do that. So it's just going to move them so that you have copies of all the changes that have gone on. Now, if you want all of that at once, if you want to actually get the edits from the file from your coworker, track it locally as well as start using it locally, you can use git pull instead. That's going to do a combination of git fetch and git merge. So we have another edit from another coworker. We pull it this time so it moves into our remote, and then it moves also into our local system. We might want that sometimes, we might not, and it depends on what your use case is. It depends on where you are in your file structure. So the open source world works a little differently, and this is why things get confusing. Because sometimes someone has created a project that you want to work on, you want to contribute to this. So there's on a file system, on a file server, we have the creator, the original, often called upstream. You have your copy of it, your fork of it, as well as your local repositories that are on your laptop. So what we're going to do is add a remote so that we can then talk to upstream. Thus far, we've only ever been talking to our origin, which is our version. This is the canonical version, our version, our local version on our laptop. So someone commits something to the main branch, to the canonical version. We want to pull those down so they exist now on our local machine. We need to push those up to our now server. And then now our local version, the original upstream, as well as our canonical version that's on the server, are all in sync. This is often called the GitHub flow, where you fork a repository, so the creator one, you pull down the code, and you create a branch locally, you make some changes, you push up your changes up to the fork. So in our case, it would be, let me go back, it would be here, and then you make a pull request over to that one. So a lot of developers will get tripped up on where code lives and where code exists in the scenario. This can be a confusing area to get a grip on. Hopefully, an understanding of both the Git history as well as how the file system itself is kind of segmented out in these three different groups will help you understand why sometimes your changes don't seem to why the changes that your coworker created don't seem to exist yet. That's because they're kind of lost. They're kind of stuck in the middle of a remote system, but not yet in your local system, and so on and so forth. All right, I don't want to bore you too much. You guys probably need a break. Next up, at the next segment of this, we'll talk about moving around Git, how to navigate around it, how to use some of the special utilities like bisect, and then some super cool GitHub stuff. So stick around if you want. If you have questions up until then, come see me, and I'll see you in a bit. 15 minutes, so we'll start again at 11:15. Thanks. You can clap at the end.
Nice red.
What's that?
Nice red. Gary,
How's it going?
good to see you.
Aren't you supposed to be talking right now?
I am in like 10 minutes.
I promoted your talk.
What's that?
I promoted your talk.
Oh, nice, thanks.
Let me turn myself off so I'm not. Maybe you just need me in other talks at some point in time. I used to work at New Relic. New Relic? No. I don't know. Do you go to OSCON? No.
That'd be a long trip.
Where do you live? Oh, oh nice. Yeah, they weren't long. I think I waited one person. And I got here at like 8:45 or 9, like right at. Yikes. How's the barbecue? How's the pit? I'm going to the pit tonight. It's good.
You going to one here in Raleigh?
Yeah, I don't know. I'm being brought there by some other people. Are like,
Pretty good.
made a reservation for going to the pit. I'm like, okay. I hear you have good, you have good barbecue here. Let's do this.
It's heavy.
That's good. It'll put me to sleep tonight then.
Yeah. I'll fall asleep right after.
Yeah. Second, it's what license do you use? What editor do you use? And then what style of barbecue do you like? Priorities. I'm about to start now.
Okay, awesome. Can I get a picture of you before you start?
Sure.
Great. Thank you very much. Is there any way you could put like a slide that has GitHub in the back?
Yeah.
Awesome.
Where was I? Let's just make sure. Slide 80. It's the only one I have that has a big enough, has a large GitHub thing.
Then I'll be out of your way. 1, 2. One more. 1, 2, 3. Great.
Sweet, now I can't see anything, so you guys are on your own.
Thank you very much.
No problem, thank you. All right. So we're gonna get started, restarted. So it wasn't entirely clear on the schedule that this is a 2-part session. Don't worry, we're able to cut it off at the right time so that if you're just diving in now, you don't have to know anything that really happened beforehand. I recommend like checking out the slides, but you're not gonna be lost going forward. So how many people are new to this session? It's a lot of you. What happened to my other half? Some of you are still here. So as a brief introduction to myself, since we don't have that slide, my name is Chris Kelly. I work at GitHub. I do a lot of outreach and speaking things about Git and Ruby and any number of things. So today, thus far, we built upon sort of looking at the Git internals and how Git functions, kind of a real deep dive in the inner workings of Git. Basically what's happening when you do things like git add and git commit underneath the file system. Come on in, don't worry. So now we're going to start looking at more high-level stuff. Basically, instead of looking at these obscure commands that you probably will never use, we'll be looking at things you probably will use on a day-to-day basis. How to navigate things, how to navigate around Git, and go from there. So the important part to remember is that Git, for the new people, is that Git is really about communication. And that's really important. The reason you're using source control isn't just to maintain your file system, but it's actually to communicate to yourself later, your software development teams, some software developer that you're contributing to their project much across the world, any number of ways. Git is really about communication. It's not about just tracking file changes. We're actually really tracking individual code changes, methods, functions, moving them around. We can go down to that level. So think about your code more as, and your commit messages more like a journal and less like I changed this file. If you reference the file you changed in your commit message, you've probably done it wrong because that stuff's already tracked. So why did you change it? What was the purpose of the change? What did it affect? Things like that. So we're going to dive in on sort of getting around Git. So thus far, we basically have some source code from other places, and we brought it down to our local file system, and we're going to start exploring it. This section is really about figuring out how to read code and how to read Git commit messages when you get to a new project. I'm assuming everybody here works at some company or works for themselves and either has to look at code you didn't write or look at code you didn't write until a year ago. So how do you read source code and source control messages in a way that allows you to get up to speed on a code base very quickly? Do you change teams often? Do you change projects often? Do you get new client work often? Are you adopting these old code bases that you're trying to do a repair job on? So how can you figure out what's going on? So that's what we're going to spend the first part looking at. So initially is the Git log. When I get a new project, whether that's I'm put on a new team or I'm working on a new open source project, the first thing I do is start to look at the log. I want to see what's been going on in the project and what sort of paradigms has this project taken on. Is it something as mundane as updating doc, or this is, by the way, this is the Ruby source code, the C source for Ruby that we're looking at right now. So how does this team function and how do they communicate? That's what we're really trying to understand when we look at Git log. So there's a couple different ways to look at logs. So you can reference an individual commit by its full SHA, so that's the 40-character bit, but you don't really need to reference the entire SHA. You only need enough to make it unique. So in the Linux kernel, you need about 10 to 12 characters to find uniqueness now. It's gotten that far out of the 40, so they still have plenty of time to find unique SHAs over time. In small code bases, 6 is usually plenty sufficient. So these all do exactly the same thing. So Git is smart enough to just match down to the level that you need it. And you don't have to worry about copying and pasting the entire SHA around, things like that. So you can also reference tags and or branch references. So we talked about last time that tags are just pointers to other SHAs. So this could be pointing to the same exact thing. So it's much nicer to remember, I want to look at version 2.3 of the code base right now. What was the state of the world at 2.3 versus what is the state of the world at that SHA, which I can never remember. So you can change the way your logs look. I have a lot of aliases, and we'll go over some of them later about how to look through your code base. So the specifics that are running off the screen don't matter, but know that instead of looking at it in a very verbose format, we can look at it in a compact format, so I can do a quick scan down and see what's going on with that. So if I want to look at an individual commit message, I can make a reference. So I'm going to show this individual one. And then you can see this is the second commit message down from the top of that log that we just looked at. So you can see I've got information about the commit, dates, things like that, the message itself, as well as the diff that goes along with it. So you can see what actually changed in the system. This is actually the same thing as git head. So in my log, the top one was my head. 1 caret back is the second one down. So that's the same thing. That's actually easier probably than trying to copy and paste. You can do these relative navigation around your commit logs. This is actually the same thing as a tilde. That's kind of nice because tilde you can add a number and then you can get yourself down 3 commits down from head. You can also do this using multiple carets. That's the same thing. But when you want to do 20 commits down, especially when we get into later when you want to scan through multiple lines of code, I don't think you want to do 20 carets and count the number of carets you've done. So tilde is a much handier format. The only time I use the caret system is when I'm just doing head tilde or head caret. Everything else is always the tilde and then a number. So get in the habit of doing that. So right now I'm looking at 3 commits down from my head. So once I've been looking at a code base for a while, I've been kind of navigating around, I've been looking at individual commit messages and things like that, then I need to start exploring what's changed. So I was working on our CEO, Chris Wanstroth, has a package for our open source text editor, Atom. and it's called Zen. It removes all of like the Chrome and lets me like focus on writing. And so he has this package, and I needed to fix something for it because it had a gutter problem. So I started working on that a few months ago, and then I kind of forgot about it. And then I'm like, I have no idea what was going on, right? Like when I'm like, hey, I should probably finish this thing. But because it's been so many months, I have no idea what I committed. I have no idea what's been going on in master since then. And so we can start to explore code by doing ranges. So what I want to do is find out how does my branch relate to master? So here we're going to see what is in fix that's not in master. So the only commit I made in this branch is one single commit. I didn't have to check out anything. I didn't have to open up anything. I can just run this one quick log command to show me what's the difference between my fix branch and the current master. That's it. One simple, easy commit. That can easily be shown this way, and I like this formatting better. I can never remember the order of the branches with the dot syntax, but this is more succinct. So this reads get log not in master but in fix. I think that's a little clunky, but the order doesn't matter. So then I can say what is in fix that's not in master. That's how I would read this. And so that's a really nice, easy way to discover what is in my working branch, what is in this fix branch that doesn't currently exist in our master branch. There was also the long format of that, which is the -- not. That's kind of clunky and ugly. I don't recommend it, but you can use it. So this gets really interesting when you're looking at multiple branches. The problem with the dot syntax is that you can only compare two branches. In our case, it was master and fix. But what happens when I have multiple branches? What if we're working on a large project with lots of developers that has a lot of code coming in simultaneously? We're looking to do a single release based upon your feature and my feature and her feature and so on and so forth. We can use this syntax, which is nice. So then we can bring those branches locally. So I can see what's in fix 2 that's not in master. So this is everything that would come together in this single commit, or in this single merge. So I can see that I've my original fix, and then my fake fix, and then I've got what's not in master. That's pretty nice. So let's take a look at the individual commit. Again, I can see all I've done here is here's my message, and then I can see what I've changed. I've changed some style sheets, and I've changed some things. Actually, I've only just changed 2 style sheets, and that's about it. So pretty simple. I made this commit about 5 months ago. I had no idea what I was doing back then or why I might have made that commit. So good commit messages would have been helpful. I'm fixing an overflow. That's a pretty decent commit message, I'd say. So before I merge this in, though, if my branch had a lot of changes in it, if it was more than just a single set of style changes, what would master be affecting when I bring this in? So we can look at that in a different way. So we can use the same syntax, but this is going to show me what's in master that's not in fix. So master had progressed in the last 5 months. People have been doing work on this code base for a while. And it's responsible of me to find out when I bring master into my branch, what am I going to be changing? Because then I can anticipate conflicts so that I don't just kind of stab at it. Oh, let's just merge this in. Oh, crap, merge conflicts. I don't know what's going on. By looking at it this way, I can read through this code. I can read through the commit messages as well as the code that's going on here to make sure I know what's going to happen when I do this merge. I think that's a really important thing, is that instead of just stabbing in the dark and then Googling Stack Overflow for a solution, that have an understanding of what's going on before you do stuff. So I really like this methodology for checking to see what's going to come into my branches before I bring them in. This is a very common one, such that what happens is I want to see what I'm going to push up into my remote. So what is in origin master that's not in head? Excuse me, what is in head that's not in origin master? So what does my local file system understand about the state of the world versus what does my current directory understand? So this is what is mirroring on the server. This is what I currently have, the commits I've added. So if I did a git push, what was going to go up to the server? That's what that's going to show me. And I think that's a good habit to get into, is to see before you push stuff to the server, make sure you understand what you're pushing there. Your coworkers are going to depend on this. Your fellow open source contributors are going to depend on this, that you understand what you're doing. So I think that's helpful. Question? Yeah, sorry, I was just cheating on that one. Yeah, so we'll go over what git lol is. It's just a log, it's a customized log format, so it's easier for me to see commit messages and whatnot. So that's color coding and all kinds of stuff. So we'll cover that. And by the way, for the people new to this session, feel free to ask questions. We've got sufficient time, so I would like to answer your questions rather than you going away confused. So. All right, so that's showing you what's going to be in, what we're going to push up to the server. So let's take a look at an individual file. So I work on Ruby a little bit here or there when I can. And so I have a tendency to be working in the GC component of Ruby right now. And so I want to see what the history of the GC file is. So I can take a look at just the log of an individual file, and this is going to give me a long log message of what's been going on in the GC component. That's kind of nice, especially if your code base, the language you're working in has a tendency to kind of not be separated into multiple files. Ruby source is written in C, and so that's very much like giant monolithic files versus like Ruby itself, which is thousands of files and little small classes and whatnot. So I can just check out if I want to find out what's going on in a file over time. I can also take a look at the messages based upon what's been going on in a month ago. I haven't looked at this in a while. Show me what's been going on for the last month. You can see there's only been 5 commits. A lot of backporting has been going on from other previous versions. That's pretty handy as well. Yikes, that's rough. You can also do these on github.com. I think hopefully this slide, good. Okay, so the URLs, you can also do the same systems. So if I want to compare what's happening in the Atom code base, again, so I can see what's in this branch that's not in master, so I can see what that branch is doing. I can use that URL. You can't see that because projectors are awesome, so we'll skip that. You can also do it in the reverse way, so now I can see what's in master that's not in that sort of long-running branch that's been poking around for a long time. There's a couple slides here that you can't really see. So this is a diff of the files. You can also do it a split diff, which allows you to see it so you can see your changes on the right, your deletions on the right, and your additions on the left. But it doesn't matter, you can't see it. Look at the slides later. They're there, trust me. Okay, so you've explored around quite a bit. You know a little bit about your code base. You remember what you were working on a few months ago. You kind of got a grasp of things. The nice thing about Git is that nothing's permanent. So once you have an understanding of what's going on in your code base, so you can just start working, right? You can unscrew up stuff pretty easily. So just go ahead and screw it up. So let's take a look at what are some unique ways to mess around with things. So obviously git status will show us what's working, what our currently working directories look like. So in this case, my world should be a playground. Like I'm working on a local file system. I'm not working on a remote checkout. So I can break stuff here and it doesn't matter. So don't be afraid to do that. Something that a previous team of mine had was this policy called Boy Scouting. What Boy Scouting means is that if you've discovered something that was broken, you found something that was some ugly piece of code, maybe a bug, that it's your responsibility to leave it better than you found it, even if it's not what you're currently working on. So if you find a chunk of code, then we would call it Boy Scout it. But that can be interruptive, right? So right now I've made some changes to some files and whatnot, but I found this bug or this ugly method that I want to refactor very quickly. So I want to fix that. So I can use the stash for that. So that's going to take everything that I've currently got either staged or pending, that's not even remotely in the system. I can remove it. I'm going to stash that up into the file system. So the stash, like everything else in Git, is just a reference. It's a series of SHAs that tell me this is what the state of the code was at this point in time. So I can pull that off and then get myself a clean working directory. So if I do that again, now I've got myself a nice clean working directory, and then I can go Boy Scout some code. So there's a couple different ways to do that. So I could be in my current working directory, nice and clean, Boy Scout the code right there, and then I can stash that as well, so that now I've got this set of changes that I need. I don't want it on my long-running feature branch. I don't want to commit it there because it's not going to get merged into master anytime soon. It's actually going to pollute the sort of the Git history that's going on as I'm working on this feature on feature X. I don't want to pollute it with like, hey, I fixed this thing in feature Y. So I want to take that and move it somewhere else. So I'm going to stash those changes as well. And you can see that now I've got two things. I've got the sort of the code I was working on, on my feature, and then the code that fixes that Boy Scouts, the sort of the bug. So what I can do is then change branches and then stash apply. And so what I'm going to do is it's going to pop off the first component on this stash list, and apply and pop are synonyms, so you can use either one. And so what I can do is then I can pop off those changes. I've moved into this other branch, let's say master. I've popped off this quick change. I can commit that and push it straight to master if your company is comfortable with that. If your company is not, then you can also create branches, right? So you can git branch Boy Scout. I can create a new branch. I can pop off things. I can move around in history. So if I've got some changes in my feature branch, that I've committed some changes, I've created a new thing. I can go back and master 3 commits. So I want to reset my master 3 commits back to hard. So now my feature branch has those Boy Scouts in it. Master branch is back to normal, so that I'm not polluting master. And then I can do this Boy Scouting branch here. And then I can check out my Boy Scout. I can then pull in any file that I want from another branch if I happen to find the fix over there. I can move things around however I want. I've been jumping around. I've been adding commits here. I've been putting things in the stash. The thing that's important, though, is that there are about 1,000 different ways to do this, and it didn't really matter which one I chose because I'm not breaking anything. I can always do git reset master to whatever commit backwards that I want. I can tell it to do it. I can force it that direction. I can also check out head if I want to get the original file here. This is nice. I can remove any sort of pending changes to this file that I might have made that I didn't like. That's a nice way to clear out my working directory, so I can just check out the original, the latest version of head of the README if I've screwed something up there. This is the same thing as git checkout without head, because head is always implicit when you leave off a branch, so you can do that. So if you want to clean up your kind of working directory and you want to clean up this README file, you can do that. If you want to throw away any stage changes, if you're like, hey, I've gone down the wrong road, I've been kind of like, it's a rabbit hole here, I don't want any of this junk, I don't need to like undo things in the file system, I can actually just force the checkout back to master, and so that will clean up everything that I've done. All my stage and unstaged changes, they can then just be wiped away, because sometimes I go down rabbit holes, that's kind of nice. That forces it to get to the new working branch. And then sometimes you've gone down this rabbit hole so far that you need to go way back, and then you can reset it. You can reset your current working directory to the head, so where was the last commit before all these changes, and that's how you're going to do that. I'm kind of blasting through these so we can get to the more exciting stuff. So if I need to go back in time, I've actually made some commits down this rabbit hole, and then I'm like, oh crap, I shouldn't have gone down this rabbit hole. Maybe I should have been doing this on a feature branch. Maybe I shouldn't have been doing it at all. I can reset head hard back past those commits so that I can go back in time and get my world back to where it began, and just lose that history. That's fine, because I'm like, this is a scary wrong path. I don't need to go down that. This is the same thing as we saw earlier when we were updating the references from the last session, where if I'm down some experiment, I can actually update to an actual reference point, a SHA rather than sort of a relative one, master or head, back a few branches, back a few commits. So I can update a ref, so now I've got a branch experiment that's now set at this SHA, so wherever that happens to be, I can do that. What's going to happen there if I'm going backwards in time? That's going to uncommit all of the things that I've done, but it's still going to retain my changes. So now you can see I have all of these changes made, but they're not committed anywhere because I've gone back in time, but I haven't actually deleted those changes. So now I can move this over to another branch if I want to. I could stash this and do something with it later as I see fit. So that's kind of nice so that you don't actually lose the work you're doing. It's just referencing it differently. Sometimes there's a world in which you've actually committed something that you want to uncommit. That's called revert. So I can revert a single commit. In this case, I want to revert that I updated the README. Sometimes you revert reverts because that's always entertaining. You can search the GitHub. You can search the open source, the code base, all the projects on GitHub, and you can find lots of commits that say revert, revert, revert. I've found a couple that say revert initial commit. I don't know why that's a thing. Like you're reverting the very first thing you ever did, which is kind of cool. Just blow the thing away at that point in time, I think. I don't know. So yeah, I think that's a better commit message if you are reverting, reverting, and reverting. It's like I just have no idea what I'm doing right now. I'm just trying to. I'm lost. I'm stuck. I'm that dog at the computer. Okay. So we've shown lots and lots of different ways to move around the file system and lots of ways to like reset files and whatnot. There's a trick that I think is really awesome here, though, that uses the stash to look at iterative changes. And I call this, again, this projector, no red. I call it the diff to the second degree. And so what I'm going to do is, instead of just diffing a file, I'm going to diff a diff. So I've got a set of changes. I'm going to make some additional changes, then only look at those secondary changes. And here's where it comes from. If anybody's done system administration work, you might have, on occasion, done some massive regexes to find and replace things, and God knows what happens. You hope you caught it all. In this case, we're going to use Defunct's Zen project again. And we find out that Zen is a project namespace that's already taken, so we need to change it to focused. That's going to be the new name for this project. So I need to see all the references to the word Zen in all of the code. So I'm going to use ACK, which is sort of a nicer grep in my opinion. I means it's going to ignore case, so I'm going to find all references of the word Zen regardless of case. Now I'm going to build this nice fun regex that's going to then use sed to replace Zen with focused. Don't worry about all the details here, it doesn't matter. But what we're doing here is going through every file, replacing the word Zen with focused. So let's see what's happened. So I've got my giant diff. Okay, from what I can tell, it looks pretty good. Everything seems pretty clean so far. So let's do another ACK just to make sure I got everything. I do an ACK, I find Zen again, but I noticed that my original regex didn't, in fact, catch any of the uppercase Zens, right? So I didn't find and replace those. I found and replaced all the lowercase versions of it. So I'm going to have to redo that regex. Now, I don't know about you, but looking at a diff that has maybe a few hundred lines of it that are changing to make sure that I caught that the capitals are also in there on the next pass seems like a pain in the ass. And I know what I'm looking for when I do this when I make this iterative change to my regex. So why can't I just look at that? So we're going to use stash for this. So first we're going to stash the first version of the regex. So it's just changing all the lowercase stuff. We're stashing that change up in as a reference in stash, right? So now our working directory is clean. We're back to the normal set of code, but we've got a saved version of it. So we're going to rewrite our regex to include an explicit case for capital Z and capital F. If anyone knows how to do this in actual regex programmatically without making your brain explode, please let me know. I tried to find it out, and it's not easy. So I did an explicit one. So now our code includes both the lowercase and the uppercase changes. But I don't want to have to look through the lowercase versions again. I know all I need to do is make sure I caught those changes for the uppercase. So what I'm going to do is I'm going to do a diff against this stash. So that's the first stash on our list. That's the original set of changes. So now I can see that inside of my changes, I've caught just a couple things, like capital Z, capital F, for example, capital Z, capital F on these as we further down. So I'm diffing the current working directory against the stash. And it's showing me the only things that have changed are the portions I added to the regex this time. If you've ever done significant regex work, I love this thing. And you can keep doing this. I can keep stashing this set and then keep iterating on my regex until I get it right. So I made sure I've caught all the different components that I've wanted. I think it's a lot easier than scanning through a bunch of lines of code and hoping I caught it all, and then crossing my fingers and deploying to production. So this is one of my favorite tricks of Git, is the sort of the diff to the second degree. So we've talked about how to move around files. We've talked about how to do the individual, like fixing this stuff, updating that, stashing this. Now we need to talk about good commit messages. How many people have ever done a commit message that looks like this? Probably everybody, right? I have. That's not a good commit message. What did it fix? Why did you fix it? What was broken? Fixed doesn't really matter, right? So if I was spelunking through some code and I saw this, what did I fix? That's a really crappy thing to either tell yourself in 6 months when you're trying to figure out what's going on, or to tell your team that something later when they're trying to figure out what's going on. So let's go ahead and reset our head up a branch so that we get rid of that commit message, because we don't want that one. We committed, fixed. We're like, we went to lunch and we came back. We felt guilty. So we're like, fine, we'll fix it. So let's commit something else. So if we just do a git commit with no message, we're going to get brought into our text editor. So in this case, I'm using Vim. So a good commit message contains two things. It contains a message itself that's about 50 characters. So in this case, the message is rename package to focused. It's under 50 characters. It's nice and succinct. It's clean. And then it includes a good description that wraps at 72 characters. So I give a description of what's going on, why I made this change, and then I've also included the regex that I use to make this change in case Defunct doesn't like the word focused. He wants to name it something else. He can actually just take my regex from my message, change out focused to something else, and then run it himself and update his own package. That's a pretty nice commit message, right? I've given the person all the information they need to then move forward with this code so that they don't have to come back and make comments on my code and say like, hey, what's going on? That's a good commit message. So this comes from the Linux kernel where Linus is very uppity about his commit messages. He's not a big fan of GitHub's pull requests because it allows too easily to do things like fixed and things like that. It doesn't enforce a lot of rules. This comes from him. This actually comes from the archaic days of GitHub or of Git, back when you were passing things around with patch files. So if we wanted to make this an actual patch file, so I could send this to Chris rather than through a GitHub pull request, I could send an actual patch. The reason it's this formatted the way it is because my message becomes my subject line, which is readable at about 50 characters in an old school, if I'm using Pine or something, or Mutt. And then I'm wrapped at 72 characters because that's the body of my email. So, it's the hipster way to do things, but nonetheless, like there's some weird historical reasons why we do 50 character messages and 72 line wraps, because we used to email this stuff around all the time. Thank God we have GitHub these days. That's not even self-promotion. Like I can't imagine sending things around with patch files and trying to sort that out. So, as I said earlier and in the previous session, changing files isn't about the file, it's about the contents of the file. And so let's say you've made a bunch of changes. You want to group these changes into logical reasons. You might have changed this file in 10, 15 different ways, in 10 or 15 different sections. You don't want to do a git add file name and then say like, hey, I fixed these things, this and. You want to actually commit these things in hunks. The nice thing is, by passing -p, I can go through this interactive mode of saying what hunks of this file change do I want to actually include in this commit message. So by doing -p, it gives me this interactive mode, and it says stage this hunk, and it gives me a whole list of individual options. So let's take a look what those are. I've omitted some of them because they're not that useful for our purposes, but Git is going to try to be smart. It's like this group of code seems like it went together. It's lived long together. You changed it at the same time, so it's gonna group things into hunks. So if you changed a method, let's call it a short method, you can say like, yes, stage this hunk and only this hunk. The 100 lines of code that are below it that have been changed aren't added to the staging environment yet. You can say don't add this to the hunk. You can split this hunk into smaller chunks if Git didn't do a very good job of selecting how much code needed to be there. And you can whittle this down. So what you do is you go through this code and say, yes, stage this, no, don't stage that. And then once you're happy with the chunks of code that you've got committed, then you actually make a real commit. And I'm only changing 10 lines in this file, 5 lines in that file, even though I have about 100 lines changed throughout all of the different files. And then you can keep going through this process. You keep going through this staging, this additive, this sort of like hunked version of adding, which makes it really nice to make logical commit messages, even though you might have gone down a rabbit hole. I go down rabbit holes all the time. I get kind of carried away when I get in code. I'm like, oh, okay, I'm changing. And the next thing you know, I look up, a half hour's gone by. I haven't made any reasonable commits, and I've changed so many things. That sucks. I could either just be an irresponsible committer to myself and say like, here I changed all this stuff, or I can take a little bit of extra time and craft good commit messages and go through and logically change these things. Because what happens if we need to revert back one of these individual changes? You wouldn't easily be able to revert one logical change because it would all be grouped together. And so either we have to just overwrite it, or we can use Git like it was intended and revert those individual changes one by one. So let's look at what our Git log might look like after that. So let's say I've hunked my stuff together into 2 reasonable commits, and I've got myself 2 nice things. So there's also another way of doing changes. So as my head has changed, as master has changed, as I've been working on my commit, I want to put these things at the top of that, right? Because I've been working along all this way. And rebase, mind you, is one of the more complex and contentious areas of Git. So if you don't get it immediately, don't worry about it. But I want to put the changes I've made at the top of the commit history, because that's where it should logically go. Because as I push this up to the server, it shouldn't show that I made a change that's 5.5 months ago to Chris's project, because I didn't in fact make it. That's when I made the code change, but now is when I'm actually making the change. So I might need to rebase a chunk of my code. So I've got all of these commits that are all set, and I need to reorder them in some way. So what I'm going to do is take the last 4 commits from head, and I'm going to interactively rebase them, meaning I'm going to move what they're going to do. Interactive rebasing has a couple different options. I can keep commits, so that's called a pick. So I'm going to save that commit. I don't need this commit. It wasn't really that useful. Chris gave me some feedback on my code, and he's like, hey, we don't really need this one. Can you squash this one to the one above? So I can squash this one, make it go away, so that this is going to squash up. We're going to keep the 3rd one, and we're going to squash the 4th one up into the 3rd. So what that's going to do is then give me this opportunity to edit my commit messages, and then I'm going to finish with I'm going to save the file, and it's going to finish the commit, and it's going to save my commit messages. So now I've got 2 commit messages, the 2 that got squashed up, and the 2 that I kept. That's what maybe Chris wanted out of the package. It's his package. He can have his commit history how he wants. Now, Git rebase can get really ugly very quickly. This is probably your best friend. You can end up in these weird states, and -- abort. If you looked at my Git history, I'd probably say it's in the top 10 commands I use in Git in Git commands. So if you ever get in a spot where rebase has gone awry and I have no idea what I'm doing, just abort and start over. Because again, Git lets you do that. You're not actually changing anything in history. Until you've actually done the rebase. So if you're in some weird state, just abort it and start over. Sometimes I make bad commit messages. I fat finger a capital there, and I might need to amend that. So if I've made a commit, I don't need to revert it. I can actually just do an amend, so I can change the message. So then you can do a -- amend. That'll open up your text editor, so that you can then lowercase your I, and then you've got a nice clean commit message. This is also a nice way if you forget a file. Sometimes you leave out a file that you meant to include in the previous commit. You can add that file and commit it and merge it back up into the one that just happened. That's probably the most common use case I have for it. Because especially when you're doing things like committing by hunk, sometimes you miss stuff. There's lots of change files that's kind of hard, like the human eyes kind of scan past stuff. So git commit -- amend is really helpful for that. So as of last session, I asked how many people knew Git was a debugger? Anybody? Other than somebody that was in the last session. Anybody used Git bisect before? One person. So hopefully, this is one of my favorite things, and hopefully you all use this for some later time. This is one of Git's most powerful features, I think. So I've got this really long commit log. Got tons and tons of file. I've got tons and tons of commits. I know back here that my production software works. I later find out that here, I find some obscure bug that I can't figure out what it is. I can't find where in the code it changed. I can't debug. I can reproduce the bug, but I have no idea where in the code it happened, and I can't figure out where that's going. Git bisect is going to help us solve this problem, because I can either scan through possibly thousands of lines of code changes to debug this thing, or I can whittle down which commit actually introduced the bug. We're going to start with 3 things. So we're going to do a git bisect start. We're going to tell Git which is a bad commit. So that's traditionally the head, because that's where we know it's not working, because I can reproduce it there. And then we can tell it where it's good. So that's a release version that I might know this bug did not exist at this point in time. So let's do that. So right now we're going to start git bisect. So we're at the head right now. So we're going to tell Git that the head is currently bad. That's supposed to be red, but this thing's colorblind, so it's brown. So then we're going to tell Git which commit is good. So we're going to tell it at this tag, v23, which points to this one down here, that our commit is good. So Git knows there are 36 revisions between those 2 things. So what it's going to do is it's going to divide up all those commits and put us right in the middle of it. And then we're going to run some test, whether that's clicking in a browser on our staging environment, whether that's running a test script that solves it. Whatever reproduces your bug, you do that. And then you're going to tell Git, what is this commit? Is this commit good or bad? So in this case, our commit was bad. So Git knows now somewhere between the good state and the known bad state is the offending thing. So now it's going to choose another commit halfway between those 2. And we're going to do the same thing. This time we did our test and we find out that the commit is good. OK, so now Git's going to go up a little bit. It's going to go up halfway through. And it's going to keep whittling this down until we figure out which is the bad commit. We found that that one was bad, so we need to go down again. And we find out this one's good. We ran our test. It seems fine. So Git now knows, because this one was bad, this one was good, then that one must be bad as well. It's figured it out for us. It's done the math for us. And we've only looked at, 6 commits rather than 36 of them. We didn't have to look at a single line of code. Git worked our way through it and told us the exact commit that it went bad. So now that I'm done, I do a git bisect reset, and I'm done. Now I know where to start looking for that problem. What changed in that file? Hopefully that commit message was authentic and had a good message so I can find out where it went wrong. That's one of the nicest features about Git that I think is probably unused. I don't use it every week. I probably use it once a quarter, something like that, maybe less. If you got a good test suite, you probably don't ever use it. But there are some obscure, weird race conditions that come up, things like that. Git bisect is a huge feature. So if I'd say you took anything away from this session, it'd be use git bisect next time you can't figure out a debugging problem. All right, so we've got all kinds of branches we've created. We've done all kinds of messes. I'm a little OCD, so I don't like to have a lot of messes around. So I want to explore which branches have done things. So I can take a look at all my branches that are available. I can find out which ones have been merged. So these branches already exist in master. I don't need them anymore. I can also find the reverse of that. I can find out no merged. So these things haven't been put into master. They might still be long-running branches. They might be experiments I kind of gave up on, and I probably should clean those up. If I try to delete something that's not in master, it'll warn me. Git will yell at me saying that it has not been fully merged. So you have to use a capital D to get rid of it so that you're certain. That's kind of nice. Here's a long little script that will go ahead and find out everything that's been merged, grep across each of them using the value for it, and then it's going to, using xargs, use that value as an argument. So I'm going to delete the local branch and I'm going to push the origin with -- delete with that local branch as well, so that my server then gets that branch deleted as well, because nobody needs them. So that's the next time you guys download my source code, all those branches go away. You don't need them anymore. So this cleans up my history. GitHub has, I don't know, 1,300 kind of active branches right now. I'm sure most of them don't need to be there anymore. They're just experiments that, if you look at the GitHub code base, it's got lots and lots of branches that don't need to be around. I think keeping a tidy Git repo is pretty nice. Don't bother writing that down. You can grab it online. So then we've got we can Git prune the origin. So we can tell Git to delete the remote branches. That'll also do the same thing. If you want to find out what it's going to do before it actually happens, you can use dry run. It's sort of a no-op, but it'll show you what it's about to do, so you don't accidentally destroy things. Now, cleanliness is next to godliness, but I think in software development world, laziness is next to godliness. Every developer I've ever known has tried to hack their way out of doing everything. I do it. Are we supposed to be done? All right, we'll wrap up very quickly. So a couple nice things is you can pass, for GitHub, you can pass a commit message, or an issue number, and you can use any of these words, and then it will close an issue automatically on GitHub. You can also close issues on other people's repos for them, so I can close that issue on somebody else's repo. A very nice feature is that a lot of CI systems, Jenkins, Travis, for example, you put a little reference that CI skips, so that when I update my README, I don't need to run my CI on it. Like, why am I running tests on a README update? So I can add that, and it'll skip the build system, which is kind of nice. We use Jenkins internally. We have a system like that. So we can do git status. That's pretty verbose. I don't need all that message. I know what most of these things are in these areas, so then I can make aliases. So -SB gives me a short status system, but I use that so often that I just want to do ST, so that's my short status message, so then I can quickly do that. I also have sort of half-working things, so I've got some stage changes, some not stage changes. I always like to, before I make a commit message, I like to see what I've staged, so that before I know what I'm doing, rather than like just poking at the dark, seeing what's happening. So I stage things, do a git diff staged, and then I know exactly what's happening. I use that so often I make an alias for that. This is what my prompt looks like. So you can look at, I can get a really nice thing about hacking your prompt is that you learn a lot about how Git works. So you can see, in order to get which branch I'm currently on, I need to use the symbolic ref head and output that. So you learn tons of like weird Git commands in order to get the things you want. So in this case, I'm outputting which branch I'm on. Currently I'm on master. I also want to find out if my working directory is dirty, so I put an asterisk star if I've got things that have been uncommitted in there. I also want to see if they've been unpushed. So if my local directory is different than my remote, then I can tell that I need to push things. So that's nice. So before I get on an airplane, I can make sure I get my code off of my laptop. Then on GitHub, there's lots of navigations for things. I don't know if you ever jump around in code a lot, but you got some keyboard shortcuts. So these are the worst. So Command T, or just hitting T, will give you a fuzzy finder on GitHub. So you can just start typing a file name or part of the path, and it can fuzzy find for you. W will let you switch branches very quickly. So in this case, I'm switching branches to a Ruby build of 2.1. And then maybe I want to find specific line, so I know I'm looking for line whatever. That's going to highlight it for me. I do it again. I can do ranges, so it can highlight a whole chunk of things for me. So now I've got all of this garbage collector method highlighted, which you can't really see. Then I can hit Y and get the canonical version of that URL, because right now it's a reference to but I want to mail this off to somebody, so I need to say like, hey, if this commit on these lines, this is where it's going wrong, so we can actually communicate about things. So there's a quick review of that. Then I say let the machines do the work. We use on GitHub, we automatically build with Travis, for example, where we have integration. So this is the Rails project. So you can see the X's and the check marks are automatically doing builds on side of Travis to see if they're passing. Every time anybody commits anything to Rails, it always gets checked. That's kind of nice. So then you can look at the Travis build by clicking on the little check mark or the X, so you can go there and see what broke. We have lots of integrations with things like Circle CI and Travis and Jenkins. It's called webhooks, which you can't see there. I'm going to skip these since you can't see them either. But GitHub has 447 teams. We communicate by team quite substantially. So you can either reference an individual, which is just like defunct, or I can mention a team like GitHub products so that I can comment to a ton of people. You can make life easier by, if you're using Gmail, we have these nice handy little things. You can jump straight to the pull request through the issues without even opening the message, which is kind of nice. So if you're using some other client, I recommend going back to Gmail. It's pretty handy. I use that pretty constantly. I use Gmail as my notification system now. I don't use the web interface anymore. So I can filter. I can do all kinds of crazy stuff here. If I do need to send a message, I can type out, good Lord. I can type out a message. I can reply to a comment right there. And send it without actually even going to the web interface. That's really nice. So last bits, so you guys can get out of here. So Git is, I think, pretty awesome. It's pretty flexible. It lets you do all kinds of things. It wants to help you be a better developer. It wants to help you communicate better. So it kind of wants to be your friend, but Git is kind of uppity, and so sometimes it's your little drunk friend. Pukes in your car, falls asleep on your couch. In that case, there's, education is the best way to deal with your drunk friends. So like GitHub training has a ton of resources. If any of this stuff seemed interesting, give that a go. And we've got all these things. And these slides will be up on Speaker Deck later this week. So you can check those out if you want reference material for what we talked about. And thank you very much.